such a long time. Forgot to put the stream on for a few days. Oops. And no one reminded me. We're all the way now in chapter 5. We are dealing with integration. We are talking about the most basic idea of integrals, and we are talking about their basic use. We are going to learn, well, we already saw antiderivatives, so now we're going to call them integrals. We already saw the most basic formulas for integrals, and now we need to see what are they used for and what the integrals are used for, and define them through limit, which is next section, and then learn properties, which is 5.3, and then learn how to solve integrals in 5.4, and then learn the most important technique called use substitution in 5.5, and that ends the course. So just 5 sections left. So what are we going to do today? Well, it's a middle school stuff, like 7th grade at best. And then you will decide whether you want to include this on a test or not, which is coming up on Monday, because it might be the grade booster if you feel like it. What we are going to do is we are going to look at the function and partition the area between the function and x-axis with rectangles. We are going to compute areas of those rectangles, add them up, and just claim that the area of all those rectangles underneath the curve is close to the actual area underneath the curve. Now, you are only computing areas of rectangles, which is multiplication, and you will be, so you have a rectangle, and the area for that rectangle is just A times B, and A and B are sides of the rectangle. So you'll be computing that, and because you have multiple rectangles, you'll be adding those numbers. So we are talking about addition and multiplication of numbers. I think you should be able to take care of that easily, right? Also, another concept that we need to know is that y is equal to f of x. So you will be plugging in x values to get the y. Done deal. So let's see what is the idea of this. So what I'm going to do now is just draw a random function. Because I'm explaining the process, I don't even need to know which function it is. And I'm going to partition one of these areas like this. I'm going to call this, let's say, xn, and this is xn plus 1. So what I mean xn, like x0, x1, x2, x3, so any one of those. It doesn't matter which one it is. You can pick x3 and x4 if you like it. So it's just a location somewhere on the x-axis. So I'll pick those, and then I draw these vertical lines which will intersect our function f of x. Now, what I need you to recall from your pre-calculus is that the heights of these points are computed when you plug in xn into the function and you plug xn plus 1 into the function. So this point here is going to be xn comma f of xn, and this point here is going to be xn plus 1 for x coordinate, and the y coordinate is given by f of xn plus 1. So all of these are pre-calculus ideas that given x's you can compute y's by plugging x's into the function. So what are we going to do today? Well, we are going to consider two rectangles that we can draw from a situation like this. I can go to the left point and draw rectangle across like this, a straight line, and you see that you are enclosing a rectangle. I'm going to erase the shading, but here is a rectangle, right? And it is a rectangle whose width, right, the base is going to be the difference between xn and xn minus 1, simple subtraction, and the height of it is when you compute xn in the function, because that's the height, the y value. So it's quite simple to find the red area, and the red area is going to be xn plus 1 minus xn, so that's like your A, and then times b, which is function computed at xn. So you are looking at in the fancy way of writing A times b for area of the rectangle, and that's the red one. To simplify this, we would call the difference between xn plus 1 and xn, we call that delta x times the function xn. There is no shortening that one. So we will also call this one left-hand approximation, because it's the left point that gets, so we call it the left-hand approximation. Then I'm going to draw a blue one coming out off of the other point, which is the right-hand point in this region. And that one will have associated rectangle that it's smaller, lower than the red one. So clearly, if I use the red one to approximate the area, I will be making error because I will be getting more area than I'm supposed to have. And if I use the blue one, I will be undershooting, right? Because there is more area than what I am actually getting. So both of these are close, but they're not exact, right? They're close. So the second one, with the blue one, area will be given as, again, xn plus 1 minus xn. That did not change because that's the difference to give us A. But now the height will be computed at xn plus 1. So it's important to know where are you computing the height. So it's still delta x times f of xn plus 1 in this case, so we are computing a point. So these are the two, and that one is going to be called the right hand approximation. So there you have it. That's technically it. That's what we're doing today. We're going to look into these two. So let's take a look at a very simple example. So say f of x is given as 2x squared minus, I don't know, 4. And we want to look at this on the interval from 1 to 5. 2 to 5. So (2x squared minus 4), we can quickly compute the value. We know that it starts at over here at -4 because that's the whole function is shifted downwards. It's not shifted left and right, just shifted down 4. And it's going to be some kind of a parabola going like this. Now, say that this is 2, and this is a little bit crooked, and this is 5. So we are asking what is the area of this piece. Now what I can do is I can draw that a little bit wider. You can always do this. And then say this is number 2, there is number 3, there is number 4, and then there is number 5 at the end. I can't draw the straight line. There. So what I'm going to do is I'm going to say let's approximate with 3 rectangles. I'm just going to make the partitions to go into each one of the whole numbers because it's easy to compute in that case. Now, how much is each one of these guys? How much is each one of the widths? 1. Because the first one is going to be 3 minus 2, which is 1. Second one is 4 minus 3, which is 1. And the last one is 5 minus 4, which is 1. So we are immediately extrapolating that delta x is equal to 1. Delta x is each one of these little widths over here, lengths. And now we are going to choose whether we want to compute the left sums or the right sums. So let's start with left sums first. We'll compute both. So left corner, draw the line. Left corner, draw the line. Left corner, draw the line. This means that I need to compute f of 2, f of 3, and f of 4 to be the heights of each one of these rectangles. So what is the area approximated by? You see area, I put the squiggly equals, right? That is approximation. So it's going to be function computed at 2 times delta x, and that's the first rectangle, right? That's this one over here. So that's our first rectangle. Then we add to that one, the height is f of 3 multiplied by width delta x again. And we add the last rectangle, third one, f computed at 4, delta x. And now we just plug values in, we compute. So that's going to be equal to f of 2. Well, you plug in 2 in the original equation. So that's 4, 8 minus is 4 times delta x is 1. Plus f of 3. 3 squared is 9 times 2 is, I was going to say, plug in. So when I plug in 2, I get 2 squared is 4 times 2 is 8. 8 minus 4 is 4. For the second one, I compute f of 3. So 3 squared is 9 times 2, 18, minus 4 is 14. Times delta x is 1. Plus, plug in 4 is 16 times 2, 32, minus 4, 28 times 1. So technically all we have is 28 plus 14 plus 4. And that's going to be 46 altogether. Now we know that because the red lines are below the function, we know that what we calculated now with using the left points is actually undershooting, because the true area is larger. We did not account for this and this and this in our calculations at all. So that stuff there, that area, is our error. Yes?
I think it sounds like a stupid question, but delta x is just a change in the x value.
Yeah, well, it's the width of the rectangle, right? From 2 to 3. Now we're going to put the cool formula up there as well.
Yeah, that's what I was waiting for.
Now we're going to take a look at the right-hand side, and the right-hand side is going to have these blue rectangles like this. So now you can see that the blue ones are going to overshoot, and we will be computing values on the other side. So now let's approximate the area using the right-hand sums. So when you are on the right-hand sum, the first rectangle means that this is its height. At that point, right there, is the height. That means that the first value we are computing is f of 3. F of 3 times delta x plus f of 4 times delta x, and then plus f of 5 delta x. Now we already have f of 3 and f of 4. We know what they are from the previous calculation. Delta x is still 1. So we have 14 plus 28. And now we need to compute f of 5. So 5 squared is 25. 25 times 2 is 50. 50 minus 4 is 46. And now we add all of the values. So we have 14, 18, and 88. Good enough. So we have two numbers now that are approximating the same area. Yes?
Can you calculate without making like three triangles? Rectangles?
There will be in calculus 2 another 3 methods to compute this at the end of chapter 7. So take calc 2 and then you learn midpoint, and you learn trapezoid rule, and you learn Simpson's rule, and then graduate math will introduce method of cubic splines. So there's going to be a lot more to this stuff later on if you pursue math.
So far, it's going to be have to with the point.
Yeah, what we are doing now are these two basic methods. You either use left point or the right point to compute the height, and that will be it. So, all right, I have to just go for a second outside. I'll be right back. So I just want to read, this is 46 less than true area less than 88. Just give me 1 second because I have to answer a question. Okay, so talking about this. So what have we achieved here? We have a function that is given to us, and we would like to. We know how to graph that function because we either took pre-calculus 1, or if it's a difficult function to graph, we go with our section 4.3 with all of those things that we have to write out and get the function solved to graph it. I mean, so now once you have the region that you want to find the area for, you can draw that region, similar looking region on the side, bigger, and partition that region. Sometimes you are told how many rectangles to use, which can actually make this partitioning really annoying because you end up with fractions. And sometimes you pick your own. So in this case, since it goes from 2 to 5, and then there are also 3 and 4 in between, it looks like that the 3 rectangles would be fine. Now, every time you draw a function, you will always be able to do left approximations and right approximations. So left-hand approximations will be the rectangles which emerge from left points. So each region here that we pick will have a left side and the right side. So the left approximations, in our case done in red, will have f of 2 as a height, and then f of 3 as a height, and f of 4 as a height. So you just compute those in a function. And the blue ones are the right ones. So if you take a look at the first rectangle, number 2 is the left point and number 3 is the right point. So the rectangle will emerge from number 3, and then from number 4, and then from number 5. So the blue ones, in this case, are overshooting, which means that the area that you get through that calculation is higher than the actual area. And the red ones are undershooting in this case. And that means that the actual area is larger than what you compute. So since one is more than area you need and the other one is less than area you need, what you do is you just claim that the actual area is somewhere between these two numbers. Yes?
And that would be the final way you write your answer.
Well, we can do better, but yes. You compute the left-hand sums, which is red. You compute the right-hand sums, which is the blue one. And then you just claim that the true area is in between these two. But if you look carefully at these two numbers are 40 units away. That is a lot. The question is, can we improve on this calculation? And the answer is yes. And the only way we improve on this calculation is by simply making it more annoying to compute. What we do is we increase the number of rectangles. As you increase the number of rectangles, the error that you are making becomes smaller. And I will draw now a large picture to show graphically how this error gets to be smaller. So let's take a look at so here is a function, again, of some kind. We really don't care what it is right now because it can be any function. And I'm going to pick this region here. So from A to B. I want to know what's happening here. Now let's see how more rectangles improve. If I do left-hand sums, remember you go to the left side, you draw a rectangle across, then you go again to the left side, you draw a rectangle across. Now observe, everything that is above function is error. So there is a lot of error there, right? Now what I'm going to do in purple is I'm going to add more rectangles. So see, now instead of having 2 black rectangles, I'm going to have 4 rectangles that I can draw from left points. So the first one will be here, the second one will be here, the third one will be here, and the fourth one will be there. So just by simply use your eyes, you see now that this part of the error and this part of the error are no longer in your calculation. So by doubling the amount of rectangles, we eliminated those 2 shaded regions as error, which means that these 2 particular error areas are no longer in your answer, and the answer you get from this calculation with 4 rectangles is closer to the true area than if you had only 2. Now if I am to put in more rectangles, right? If I put more rectangles, so let's use green, for instance. So that's going to now partition, and I will have 8 of these. If I have 8 of these, observe that the left-hand sums will do this. And if I try to just make this a little bit larger, maybe when you review the video, you will see that now this region is no longer your error. This region doesn't exist as error. This region doesn't exist as error. This region is still there. This one is not there. This one is not there. So you see that it gets even better. So how do computers and machines compute this? Well, they're very primitive. They're only computing addition, subtraction, multiplication very quickly, which means that they can compute as many of these as you want fast, so they do 10,000 of these rectangles in a split second, right? Now 10,000 for you would be some work, so you know, generally on exams you look into, I don't know, 4, 6, 8. We like to stick with even numbers because of the fact that in calculus 2, one of those that I mentioned, Simpson's rule, only works if you have even numbers. But you can have odd numbers for any other, so there's no reason not to have. So I started with 3 rectangles. Right. So I'm going to write here in red statement, more rectangles equals better result. What I mean is more accurate. Better approximation. Use whatever words you want. I did not check the stream. Stream is working. Great. All right. So that's what we have for this. And now we just do another example, and we're done. There is nothing else for this, and we're going to use these concepts in the next section, 5.2. We're going to do that tomorrow. Not tomorrow, Monday after exam, 5.2, where we're going to use this concept and concept of a limit to define the integral, which is going to be that antiderivative we did in 4.9. So I'm just going to go quickly into the homework section and pick any of the problems, solve one. And one thing to understand is, because we are not doing derivatives, we are not doing limits, we're not doing integrals, nothing of calculus sort in this case, you can end up with any function under the sun. And you still be able to do it, because all you're doing is you're plugging in x values in a function to find y's and multiplying those by the width. Oh, maybe I should generalize also the delta x. So delta x over here, for any one of these, if it's evenly spaced, is b minus a divided by n. It's a simple average of all, right? You take b minus a, which are the endpoints, and you divide that by number of rectangles you have. So earlier I had 3, so 5 minus 2 was 3. 3 divided by 3 was 1, so delta x was 1 at all points, at all times. So here's the large version of it. So b minus a over n is the way for us to find all those delta x's. So let's take a look at any of these functions. It really doesn't matter. They say let's go with f of x is equal to 1 over 2x plus 1 from 0 to 8. And they tell you that you should use 4 rectangles. Now, the cool thing about the whole deal here is that it really doesn't matter whether you know or you don't know how a function looks like. That's not important at all. As long as you have some kind of function that starts at 0, 2, 3, 4, 5, 6, 7, 8, and ends at 8. This is your f of x. I know that this is not the exact function graph. I put whatever. I'm only interested in these rectangles. So I need 4 rectangles, so that's divide in half and then divide in half again. I need this graph over here for visual, because I need to know where I'm computing my functions. For the left sums, I will be clearly computing at 0, at 2, at 4, and at 6. And for the right sums, I will be computing at 2, 4, 6, and 8. So area is approximated as f of 0 times delta x plus f of 2 times delta x plus f of 4 times delta x plus f of 6 times delta x. And since we are doing the left-hand sums, we are not going to use f of 8 because f of 8 is not left for any of the rectangles. In order for f of 8 to be the left, you need to have a rectangle on the right of it, but we don't. So now, to compute this, f of 0, you simply plug in, well, first let's go with the delta x calculation. It's obviously 2, but let's calculate. 8 minus 0 divided by 4, right? B minus A divided by 4 rectangles. It's going to be 2. So delta x is 2. And you can also see the delta x is 2 from the picture, right? Because delta x is the width of each one of the rectangles. It's evenly spaced. So we simply start with f of x 0. So plug in 0 in the equation. We get 1 times delta x, which is 2, plus f of 2. Plug in 2 over there, so it's 1/5 times, again, delta x is 2. F of 4, that's 1/9 times 2. And then 6, 12, 13, 1/13 times 2. So this, you see, it's just annoying calculations. It's nothing difficult, I hope. 2 plus 2/5 plus 2/9 plus 2/13. And that's going to equal a number eventually. 1/2x plus 1. So I'm just going to cheat and put all of these in the calculator so we don't have to stay forever. And I get 2.776. Now I will compute the right sums, which means the points on the right are in charge, which means that the area is approximated now by f of 2 delta x plus f of 4 delta x plus f of 6 delta x, and we have all three of these. And the new one is just f of 8 delta x, because now if it's the right hand point, the rectangle is to the left of it. So we do have f of 8. We don't have f of 0 this time around. We already know the values for the first three. There are 2/5 plus 2/9 plus 2/13. And the only one I need to compute is 8. So 2 times 8 is 18 plus 1 is 17. So 1/17 and then 2, so 2/17. The second one is always quick to compute because you have everything. Now what I'm going to do is use the previous calculation. I'm going to take off 2 because that was f of 0, and I'm going to add 2/17. And we get 0.894 if you round properly, and you just claim that the actual area is somewhere between 0.894 and 2.776. So technically about 2 units, right, the range of 2 units to compute this. So that's 5.1. There is also another piece that is introducing sums and how those sums work, but I'm going to keep that and present that together with 5-2, because it should belong with 5-2, because we do Riemann sums, which is the limit definition of integrals. We do that in 5-2. So I'm just going to hold off on that part and introduce it after the exam on Monday. So that ends the section 5.1. As you can see, all you're doing here is computing the areas of rectangles by multiplying width times height. Heights are computed as f of x, and the widths are all delta x's, which is b minus a divided by n, which is the number of rectangles. I promised 7th grade math. I believe that the 7th grade math is delivered, and you can decide whether you want to add this for the Monday's test or not. That's up to you. We'll see. So that's it for the stream. We'll resume after the test on Monday.